Welcome to Study Loop.
This is the answer to Chapter 17, problem number 45 from the Smith Organic Chemistry textbook. And in this problem, we are asked to draw all reasonable resonance structures for pyrrole and explain why pyrrole is less resonance stabilized than benzene. And then we're asked to do the same thing for furan. Okay, and so these are going to be very similar. They're obviously the nitrogen and oxygen. They're equivalent with just different heteroatoms, is what I'm trying to say. And so to make the resonance structures, we can start like this. And actually, I believe we had to do this in a problem right before this one. So, yeah, so it should be familiar. Okay, and so nitrogen has a charge here. It has a positive charge, and now our lone pair and negative charge are located on this carbon. And then we can move it one more time. So the electron movement would look like this. So these can go here, and these will then go here. And so, again, we have a positive charge on the nitrogen here, and we have our lone pair and negative charge on that carbon to the left. And then we can draw another set. So here's pyrrole again. And we can do the exact same thing, just moving the other way. So like this. To get to here. So lone pair, negative charge here. Nitrogen has a positive charge on it. And then the electrons can come here, and these electrons will go here. And that is going to get us to our last resonance structure, which will look like this. And again, positive charge on nitrogen, and now our lone pair and negative charge are here. And so pyrrole is less resonance stabilized than benzene because all of these resonance structures, other than the starting pyrrole, have charges. And so it's the presence of charges. So charges are less stable resonance structures. So benzene, with its resonance structures, there aren't charges. There's no charge separated form. We just move double bonds around, and all the atoms stay uncharged. And so that's considered better. It's considered more stable. Yeah. Okay. And then so we're asked to do the same thing for furan. And again, it's going to look exactly the same, just with an oxygen instead of a nitrogen. So not exactly the same, but very similar. So the oxygen is going to have two lone pairs. And so we'll just do, the same thing. One of the lone pairs will add in here. This bond will break to get us to our first resonance structure. So oxygen is now going to have only one lone pair and a positive charge. And we will have a lone pair and a negative charge on this carbon. And then again, just like pyrrole, The electrons are going to move like that. And so that's going to take us to here. And so we have a double bond here and a double bond here. And so again, the oxygen's only going to have one lone pair, and it'll have a positive charge on it. And the lone pair is going to be on the left carbon there. Yeah, okay. And then again, we can do the same thing moving the other way. So starting back from furan, so 2 lone pairs on the oxygen. And then we can, as I said, just do the same thing moving the other way. So first resonance structure, looks like this, with a lone pair here, 1 lone pair and a positive charge on the oxygen. The electrons will move here. And so our final resonance structure will look like this. Double bonds here and here. Lone pair and negative charge, and a lone pair and a positive charge on the oxygen. And so the reason that furan is less resonance stabilized than pyrrole, so oxygen is less basic than nitrogen. So the lone pairs are donated less willingly, and since there's not as much driving force there. So let's say that the lone pairs are less delocalized. So since they're less delocalized, these charge-separated versions, these 4 resonance structures that we drew where there's a positive charge on the oxygen and a negative charge and a lone pair on one of the carbons, they contribute less to the resonance hybrid. And so there's really less resonance going on. And so furan is less resonance stabilized. And that's the answer to chapter 17, problem number 45.